For a long time, humans have imagined what life could be like in other universes. Thanks to the James Webb Space Telescope, the most advanced telescope in existence, that question can finally be explored by examining the nearest star system to our own, Proxima Centauri, which is located just 4 light-years away. Scientists have detected several unusual anomalies from one of the planets in the system, Proxima B. These oddities, known as false lights, have left some of the greatest minds in science astounded. But what do they mean? Could these lights be evidence of intelligent life on the planet? Join us as we investigate the James Webb's surprising revelation of city lights that might alter everything. The only known life in the universe is on Earth. Since the beginning of human civilization, people have wondered whether life exists elsewhere in the cosmos. To embark on such an interstellar search, American astronomers Jill Tarter and Thomas Pearson initiated the search for extraterrestrial intelligence, SETI project in 1984. The aim of this nonprofit initiative is to capture spaceborne radio signals. Radio waves can travel great distances and are therefore more likely to be detected by the 42 radio telescopes that form the remarkable Allen Telescope Array in the mountains of California and the Sierra Nevada. However, over the past 30 years, no definitive extraterrestrial signal has been found. Following the successful launch of the James Webb Space Telescope, the mission to explore a variety of unseen planets orbiting far-off stars was given a boost. As the largest telescope in the world, positioned nearly 1 million miles from Earth and outfitted with extraordinarily sensitive detectors, it holds the promise of making groundbreaking discoveries. 20 years ago, there were no known planets beyond our solar system, but since then, more than 4,000 exoplanets have been identified, each orbiting different stars. According to NASA, the universe may harbor trillions of exoplanets. Some of the earliest signs of something unusual beneath the surface of our solar system might be found in extraterrestrial plant life. The Galileo spacecraft, on its way to Jupiter, turned its instruments back toward Earth and detected a distinct signature of plant life known as the vegetation red edge, an interplay of red and infrared light reflected by plants. For example, a planet like Earth, covered in a lush jungle, should produce a clear and unmistakable V signal. The James Webb will measure the V of distant, Earth-like planets in the habitable zone around their stars, offering valuable clues to what might be occurring beneath their atmospheres. When sunlight passes through a planet's star, the James Webb may be able to detect it as it enters the planet's atmosphere. Missing frequencies can then be identified through spectroscopy, as particles and atoms in the atmosphere absorb specific frequencies, creating a characteristic signature that the JWST can recognize. This technique might be used to determine the composition of the atmosphere and assess whether life is feasible. Life could exist on Earth-sized planets with atmospheres similar to our own, composed of a mixture of oxygen, nitrogen, and carbon dioxide. By searching for substances that are not typically found in such atmospheres, scientists might detect the presence of intelligent life. For example, chlorofluorocarbons, CFCs, chemicals used in refrigeration and cleaning, would likely be noticeable to observers studying Earth's atmosphere from a distance. If the James Webb detects CFCs on other planets, it could be a clear sign of a technologically advanced civilization. However, life on exoplanets might not resemble life on Earth at all. Sometimes even naturally occurring organisms, such as extremophiles, species capable of surviving in conditions that would destroy most other forms of life, might seem alien. These microbes can endure extreme environments, such as temperatures as high as 250 degrees Fahrenheit or extremely acidic conditions with a pH under 3. Since planets like Earth are more likely to support life than those with extreme heat or acidity, it might be sensible to begin the search with planets that have more temperate conditions. Prime candidates might have temperatures that allow for liquid water to exist and orbit stable stars. Our Sun is a yellow G-type star, which is rarer and tends to have shorter lifespans. However, in our universe, planets around red dwarf stars, which are more common and have lower luminosities and temperatures than the Sun, are more likely to be studied. These longer lifespans increase the chances for life to develop and evolve complex organisms. Around 40 light-years away, the TRAPPIST-1 planetary system will be the focus of the James Webb's first mission. It orbits a quiet red dwarf star and contains 7 Earth-sized rocky planets. 3 of these planets, located in the habitable zone, could potentially have liquid water on their surfaces. Despite its smaller and colder mass compared to our Sun, the TRAPPIST-1 star emits light similar to Earth's. Due to the close orbits of its planets, Proxima Centauri, a red dwarf star located 4.25 light-years away from the Sun, may be the most promising location for observing city lights beyond our solar system. Proxima is much dimmer than the Sun, so a planet would need to be much closer to it than Earth is to the Sun to maintain liquid water and support life. In August 2016, cosmologists discovered a planet with 1.3 Earth masses in the habitable zone, a Goldilocks zone where the light intensity is perfect for melting water. Proxima B orbits Proxima Centauri, but it's possible that it is an airless, dormant planet because it orbits its red dwarf star at a distance of just 4.6 million miles. This close orbit exposes the planet to powerful solar winds that could strip its atmosphere away. However, Proxima B still receives enough sunlight for liquid water to exist and potentially conditions similar to Earth. Due to its proximity to the star, Proxima B is believed to be tidally locked, meaning it always shows the same side to the star, much like the Moon does to Earth. Proxima Centauri has only 18% of the Sun's mass and emits significantly less light than expected from a star this close to its planet, just 5% of the Sun's brightness. It might seem like a desolate, lifeless world, but liquid water could still exist on Proxima B if it retains an atmosphere to trap heat, even though it only receives about 65% of the sunlight Earth gets. However, the planet's conditions are not very conducive to life. Its likely tidal locking means permanent day and night cycles with extreme temperature fluctuations. Additionally, the planet receives 100 times more high-energy radiation than Earth, including X-rays and ultraviolet radiation, due to its proximity to Proxima Centauri. If it does not have a protective magnetic field like Earth's, these harsh conditions could make life impossible. Despite these obstacles, real-world conditions could still render Proxima B a potentially promising planet. Unfortunately, simulations suggest that the atmospheres of tidally locked worlds are prone to rapid degradation, especially due to the freezing of volatile gases on the planet's dark side. Earth's atmosphere is replenished through volcanic eruptions, and planets with robust magnetic fields are less vulnerable to atmospheric loss. Given our limited understanding of Proxima B's volcanic activity or magnetic field, it's difficult to predict whether it has an atmosphere. However, if Proxima B does possess one, it might suggest the existence of oceans, and together these characteristics could point to the possibility of life. We're eager to learn whether Proxima B harbors a diverse ecosystem. It could even feature solar panels on its sunlit side to generate energy, helping to keep the night side warm and illuminated, which would otherwise be extremely cold and dark. The discovery of Proxima B has sparked a race to determine whether the planet transits its star's surface. From Earth's perspective, such transits would allow astronomers to measure the planet's dimensions, mass, and density, which could confirm its rocky nature. By analyzing the light that passes through its atmosphere during a transit, scientists could gain insights into its atmospheric characteristics. However, the chances of such an alignment occurring are only about 1.5%. The star's propensity for flaring further complicates the task. Astronomer David Kipping from Columbia University has observed that stellar flares can cause rocky planets to absorb sunlight and re-emit it as infrared radiation. However, rocky planets around stars like Proxima Centauri emit a distinctive kind of infrared radiation. The James Webb Space Telescope, JWST, is specifically designed to detect such infrared light, which makes Proxima B's infrared signature crucial for identifying its atmosphere. Additionally, infrared observations offer clear advantages over the Hubble Space Telescope, potentially allowing the JWST to detect faint artificial lights on Proxima B's night side. Proxima B's sunlit side might be covered in solar panels that reflect starlight. As Proxima B orbits its star, it experiences a constant cycle of day and night, with stark temperature contrasts between the two. The temperature differential depends on whether the planet possesses an atmosphere. Without one, the day side would radiate all the energy it receives from Proxima Centauri as blackbody radiation, leaving the night side frozen. If the temperature variations are less extreme, this could point to the presence of an atmosphere. Conveniently, It will take the JWST just 11.2 Earth days to measure the infrared radiation from both sides of Proxima B after it completes an orbit around its star. If Proxima B does have an atmosphere, the next step would be to analyze its chemical composition. The presence of gases like oxygen, water vapor, and methane could hint at the potential for habitability or even life. However, this task is not straightforward, as scientists must capture starlight that either reflects off or passes through the planet's atmosphere. While the JWST is capable of studying some of the closest potentially habitable exoplanets, it was not specifically designed to search for extraterrestrial life. It is limited to monitoring fluctuations in methane, carbon dioxide, and water vapor levels. The JWST cannot detect free oxygen, which is a key indicator of biological activity. Though some gas combinations might still suggest the presence of life, one of the ground-based observatories poised to perform more in-depth atmospheric analyses is the Extremely Large Telescope, which is expected to be operational in the 2020s. Ozone could be one of the substances detectable by the JWST. Until these new telescopes become active, the JWST will continue providing valuable data for analysis over the coming decade. In addition, future space telescopes may use innovative techniques to block out the intense light from a planet's star, focusing instead on the faint light from the planet itself. This could be achieved using small internal masks or large external satellites designed to obscure starlight, making it easier to study distant worlds. Regrettably, many of the gases associated with life on Earth can also be produced by non-biological processes. For example, methane is generated by both livestock and volcanic eruptions, and sunlight can convert water molecules into oxygen and hydrogen through photosynthesis. Searching for extraterrestrial life is likely to result in some false positives, and space scientists will need a comprehensive understanding of a planet's environment to rule out non-biological explanations for certain gas signatures. The next phase of planetary exploration could provide the compelling evidence necessary to confirm the existence of extraterrestrial life. The fundamental data provided by the James Webb Space Telescope offers us a glimpse into what the future may hold. If life exists elsewhere in the universe, it could answer one of science's most profound questions. Is life abundant throughout the cosmos, or are we truly alone, confined to a solitary planet in the vastness of space? Regardless of the answer, such a discovery would lead to profound shifts in our philosophy and worldview. The quest for extraterrestrial life has inspired generations, sparking countless theories and stories. As technology advances, our understanding of the universe deepens, opening up new possibilities for life beyond Earth. The James Webb Space Telescope not only enhances our ability to detect distant exoplanets, but also enables scientists to study their atmospheres, potentially uncovering signs of life. The search for exoplanets fosters global cooperation among scientists and space agencies, pooling resources and knowledge to increase the likelihood of groundbreaking discoveries. These collaborative efforts also heighten public interest in space exploration, stimulating curiosity and imagination worldwide. In the end, the discovery of extraterrestrial life would challenge us to rethink our place in the universe and our relationship with Earth. As we refine our technology and techniques for exploring the stars, each new discovery brings us closer to answering the age-old question: are we alone? The journey ahead is filled with limitless potential, inspiring the pursuit of knowledge beyond the boundaries of our planet.